1 second. Yeah, now.
Okay, I think it works. Okay. So again, welcome to this session. So this is the last session
Excuse
of.
me, there is a background noise. Is it
I
only
know
me?
because some people came to mow outside my apartment. Sorry about that. It will
Okay.
not take long, I guess. But
Okay.
the disadvantage of working from home in these days.
Okay, no problem. You can
Yeah.
continue. Sorry.
Yeah. Thank you again for attending this workshop. So this is the last session, and in this session we have two great talks. The first talk is by Dr. Swami on adversarial machine learning, so it's my great pleasure to introduce Dr. Swami. He is with Army Research Laboratory and is the Army's senior research scientist for network science. Prior to joining ARL, he held positions with Unocal Corporation, the University of Southern California, CS3, and Malgudi Systems. He was a statistical consultant to the California Lottery, developed a MATLAB-based toolbox for non-Gaussian signal processing, and he has held several visiting faculty positions, he received his BS degree from IIT, MS degree from RISE, and PhD degree from University of Southern California. He's working in the broad area of network science, and he's an ARI fellow and a fellow of the IEEE. Today, his talk is on adversarial machine learning. And thank you very much again for accepting our invitation. I stop sharing at this point. Okay, I think Dr. Swami can share his screen. Okay, good.
Hi, good morning, good afternoon, good evening, as the case may be. Hulya, thank you very much for the introduction and also for the kind invitation and this opportunity to talk a bit about some of the work we're doing in adversarial machine learning, federated machine learning. Thank you for this opportunity. As I said, I'm at the Army Research Lab, but anything I say, of course, is my own opinion. They do not reflect any official policy opinions of the lab or the Army. And the same vein, if I use any commercial product names, they're not to be taken as any endorsements. We have already had a few papers this morning touching on deep learning, particularly in the context of 5G, 6G, as well as estimating CSI. Professor Junsheng Zhang gave a great talk just before the break, where again he was talking about aspects of what he called meta-federated learning. And I know that Professor Jennifer Chen, who's right after me, will be also talking about adversarial machine learning, more in the context of audio and speech. I will not be touching upon that in this talk. So my own background, as back in school, was much more on robust statistical inference, statistical communication theory. So there we were worried more about postulating good distributions, learning distributions from data, and then setting up robust hypothesis testing procedures. But here, of course, in this modern idea of dealing with data directly, we don't do that, right? We don't learn joint distribution explicitly. We don't do certain statistic feature extraction and so on. So in the next 45 minutes or so, I will give a short overview. And of course, this is a biased overview, clearly. The sampling always depends upon the sampler, I guess. And I'll talk a bit, obviously, about some of the work in which my group has been involved. So let me first thank my collaborators at ARL, Kevin Chan, Brian Jalan, Gunjan Verma, with whom I had a collaboration on this topic of adversarial federated, but also on other topics as well. I've also been very fortunate to be involved in multiple ARL partner programs. The US, UK, and ICITA, for example, the joint work with UK. And here I've been fortunate to work, for example, with Shi-Chan Wang and Dinesh Verma from IBM US, Tinga and a group at Penn State, Richard Thompson at IBM US, IBM UK. The cybersecurity CRA is another partner program. I've had the fortune to work with Petri McDaniel and Nicola Papernov, and still a grad student at Penn State. And also the group at UC Riverside, led by Srikanth. And I've talked a couple of works I've been involved there with one of the grad students there, Shasha Lee. IABT CRA started a couple of years ago. And again, I've been fortunate here to work with great people, the three Jars, Sumit Jha at SRI, Susmit Jha at SRI, Sumit Jha at UTEP, and Sumit Jha at Wisconsin. I mean, anyway, I've been very fortunate in my collaborations, both with seasoned researchers as well as with grad students. So going to the next slide. So this headlines, all of you know about this headlines. You all seen this and other variations of it. We heard bits and pieces of it alluded to in the talks early in the day. And of course, if you look at what DeepMind is doing now, so beyond AlphaGo, they want to try and redesign new games of chess, I guess, trying to make it perhaps even more complicated. So there have been a lot of successes in the past, right? 4% accuracy, 4% error rate, 95, 97, 98% accuracy, on all kinds of stuff, particularly in image object recognition and speech speaker recognition. So, but of course, this comes with a lot of small issues, right? I mean, those numbers of 96% accuracy, they are aggregate performance on standard data sets. But if you look underneath, you find a slightly different story behind the aggregate numbers. So what I'm showing on the left-hand side is a panel taken from this nice paper by Samuel Dodge and Lisa Karam at ASU, published back in 2017. And what they did was they said, okay, let's take some standard images, let's add some noise, some blur to it, show it a bunch of humans, and then give it to what is then standard VGG16 object recognition system, and then look at performance. So showing you just one panel out there with 4 examples. The correct labels are shown on the left-hand side, and then the degraded image is shown on the right-hand side. And the prob human, that the green column is what 90+ % humans classified this as. And then on the right-hand side is what VGG16 classified it. Right? So this may seem anecdotal, but on the right-hand side, I'm showing you essentially accuracy versus amount of perturbation. Top is noise, bottom is blur. I'm showing you multiple curves. The red curve is what the human-aided recognition, or I should say human classification. And the next 4 curves are VGG, Google Lens, ResNet, and their fine-tuned version. What do you mean by fine-tuned? So you train the network on what the degradation is. So the top one for noise, and the bottom one for blur. And then regardless, you don't do very well. So question here, of course, is that you don't get good robustness, right? You don't have good notions of uncertainty quantification. A part of the reason, of course, we know is that we learn semantically, right? The machines don't do that. I mean, by and large, they build implicit statistical models. There's, of course, a growing interest in trying to push the machines to doing semantic knowledge representation, semantic learning. An example I'll give you is of a new research effort that Ahmed Research Office started at UPenn. So MURI, led by Insup Lee, Dr. Purish Iyer is the PM for that. So there the question they're looking at is, how do people learn? How do people form semantic ontologies? And can you use that to guide machine learning? Of course, that effort just started, so it'll be a couple more years before we come. So of course, if you talk about adversarial, you got to show the panda given picture, right? I mean, I'll come back to this 57-99% confidence numbers a little bit later. So of course, in the old days, by that I mean the 80s, the 90s, when people were working on image classification, they dealt with textures, they would do pre-processing, and by and large, the standard image then was Lena, and then of course they had textured images. But now, of course, everybody looks at panda given, right? And of course, if you worked in network science, you probably use Zachary Karate Club for as a benchmark data set. So top one is this, now extremely famous paper by Zagiri et al. That basically showed that you could take a standard picture, add a bit of noise to it, and your object recognition system goes completely haywire. And of course, this is not true just for, it's not just a one-off case. So showing you some results from a paper that we did Patrick McDaniel's group back in SSP 2016. So showing you two panels, one is black and white images, the MNIST, the bottom is CFAR10, so color images. In each, the top panel shows you the unperturbed image, and the bottom shows you some kind of perturbation. Here, of course, some kind of bounded norm perturbation. And then the labels at the bottom show you what the classifier says the correct label. So the 0 with a bit of noise get misclassified as a 5. The dog gets misclassified as a bird, and so on and so forth, right? So you can do targeted misclassification, and you can do also general misclassification. This was in terms of L infinity, L2 norm perturbations, but there have been other works by other folks. For example, Jave Su at Kyushu had this nice paper back in 2019, and what they did was they said, I'm going to attack one pixel. I'm going to change only one pixel, because maybe a slightly complicated optimization problem to solve. But I'll change one pixel so as to make the classifier do to make the classifier misclassify. I'm showing you here results on 3 different classifiers, and that's what the 3 columns refer to. And then the classification results are shown, and the percentage is essentially what classifier thinks is a measure of confidence. And I'll come back to confidence a little bit later, right? What's a good measure of confidence and what is not. So these are for images. What can you do with video? So you had a paper with Shrikant Kushmiti's group at UC Riverside. Shashali is the lead author, grad student out there. So presented at NDS 2019. The question we asked was, so supposing a video, and I don't quite know how to do the frame synchronization, but I want to perturb the video so as to, again, do targeted misclassification. So can I do that without really knowing the content of the video? Because I want to do real-time adversarial attacks, so I may not have time to look at the video clip, analyze it, and then perturb it. And what we found was, indeed, you could develop what we call universal cyclic, in this case, perturbation sequences that can add an arbitrary video clip, at least a class of video clips, and get successful adversarial attacks. We tested a couple of data sets. This is the UCF gested data set, as well as the gested data set. So 2 different kinds of data sets. But perhaps the earliest work on adversarial may have been the work by Darby and all. They had it at KDD 2004. They were interested much more in email spam, right? But some of the ideas there apply to what we want to do now, right? So in some sense, all of these examples I've shown you, we were able to manipulate images directly, and there have been other work also on manipulating text directly or manipulating video field directly. So this in essence means that the adversary is already in your system, right? Adversary access to your camera or to your video feed, to your email feed. So perhaps that's a little bit of a, what we'll say, very powerful adversary. So then one could ask, are these realistic? And let me give you an example out here. So this is on physical attacks. I took this slide from a talk that Dr. Howard Siegelman gave at DARPA Guard Proposes Day a year ago. So DARPA Guard started only this year, with a bit of a delay. Dr. Bruce Draper is running it now. So Guard is interested in understanding what kind of defenses can you have for our adversarial attacks, looking both at digital as well as physical attacks, and eventually also wanting to look at not just single mode, but also multi-mode attacks, right, and defenses. So the top row shows a stop sign and then a carefully added patch, which causes the detector to classify it as a speed limit sign. And I know that most of the audience has seen examples like this before, so I will not belabor the point too much. The second example, the second row shows a tank, patch is added, and then suddenly it looks like ambulance, right, or a school bus. The third example comes from Metzen et al. And Bosch, and they're looking at this cityscape images. And that idea was again similar. Can I add patches or perturbation so as to make things invisible, things disappear? And there have been subsequently other work where you see an image of a classroom and then suddenly the professor disappears because she's wearing a t-shirt with some interestingly, what should I say, created imagery or a patch. Right? And so this also all of this says that, yeah, these things can be real. Let me show you an example that was reported recently in MIT Tech Review back early this year. So these folks from McAfee, Povolani and Trivedi, what they did, they put a 2-inch strip. I think it's a physical patch attack, right? It's a patch attack. And they tested on 2 different cars, and both the cars in this particular case, Tesla, but that's just anecdotal, right? I mean, think of almost any other self-driving car. So they put it on a 35-mile-per-hour speed sign and is interpreted as an 85-mile-per-hour zone. And of course, the cars accelerated accordingly. Interestingly enough, I guess there are enough safety mechanisms built in these cars. They only went up to 50 miles. They did not go to 85 miles per hour. So I guess there is some other savings grace out there. And of course, there have been other attacks have been reported. Science magazine had an example last year, March 2019, from Finlayson and group at Harvard, MIT, and they were talking about attacks on medical machine learning, right? And so there, of course, you can imagine what that might do, a misdiagnosis or a bad diagnosis, right? So there's a lot of opportunity here for mischief, and we need to develop good defenses. So what are the Army context for this? Why is my lab interested in this? So just showing you a mock-up scene of a urban battlefield, if you will, and you can think of multiple things out here, right? I mean, you could have some kind of precision engagement that goes from, let's say, a helicopter or UAV to some targets of interest. So this needs to learn on the fly, needs to do target recognition very quickly, right? You may have autonomous UAV swarms. They need to do flight planning and replanning, again, on the fly. You might have a soldier equipped with AR, VR, and could also have wearable electronics. You might have human autonomy teaming, so humans and agents teamed up. And overall, you might, of course, have all kinds of devices, IoBTs, things, sensors, intelligence services. So very complicated network. You need to intelligent network management for this. And the assumption, of course, is that the adversary is a peer adversary, sophisticated, will employ deception, right? And there'll be persistent threats from this adversary. And the other issue, of course, is the environment is constantly changing. We don't operate in the same environment, right? So we need to adapt quickly. So a lot of gaps in this. Classified them into 3 main categories. So first is what we call learning in complex data environments. So what's the issue here? So much of what we are seeing with this ImageNet or other kinds of data set, these are well curated, right? Millions of samples, carefully curated data. But most of the time, what we have to deal with in the field are small samples or data sets. Data largely dirty, data largely cluttered. Example, of course, is we don't necessarily have pristine pictures of missiles that adversaries have, right? And of course, the other issue is that data heterogeneous, not just image, but you may also need to deal with other kinds of data, text data, unstructured data reports, and so on. The environment deal with will be contested and deceptive. So it means we have to learn in a very complex environment. The second issue that this learning has to be done at the point of need, and at the point of need, we're extremely resource constrained. For example, communication will be very limited. The pipes are very thin, which means you don't have the time or the opportunity to go back to a server that has all kinds of models available for use. We also the safety issues, right? Low size, weight, power, which affects both computing, storage, and communications, and also the time available to make a decision. You don't have time to send it up to a cloud, wait for sophisticated processing, wait for the results to come back. And the last bit is about generalizability and predictability. So if you have very little amount of training data available, then you hope that you learn well and that what you learn can be generalized into a new learning context. And of course, explainability is important because it enables, for example, human agents to team, enables learning in heterogeneous environment, trust in a collision environment. DARPA has a huge program. This, of course, XAI, which we are tracking. Excuse me. So, give you another motivation. So, we can look at attacks on learning systems in a bunch of different ways. One could think of data poisoning attacks. So, this is when the data at training time are manipulated. Example could be in a crowdsourced data gathering environment where you don't necessarily have control over all the different sources of data. And second is in collision operations where you may be getting data feeds from sensors that we don't control, we don't own, we don't control. So there's scope for manipulation out there. There's, of course, the attacks on privacy or training data disclosures. And this again comes about, for example, you may have information sharing constraints. You don't want to disclose the data on which you trained. So you need to be careful about those attacks as well. And what I'm going to talk today mostly is the third class, which is the so-called adversarial example synthesis. So this is when data at operational time or test time are manipulated so as to cause targeted or general misclassification or just lower the kind of confidence you have. So why this is important? So the previous one, I showed you the picture of a tank with a patch, right? A tank with a patch or tank with some kind of NOS added to it. It gets classified as a burning school bus. I leave the implications of what reactions that might be, right? You go to say a burning school bus, or you realize it's a tank and you take appropriate actions. So why is it easy to create adversarial examples and why are we worried about it? So much of the standard assumptions are here, right? The fundamental assumption in most statistical learning is that the data IID, independent identically distributed. And more importantly, that the training and test data come from the same distribution. So let's say a couple of examples, the UCA opt digits data sets. So apparently the consecutive samples there are likely to come from the same writer of the data set. The samples are not distributed because consecutive sets will suffer from the same bias because they come from the same writer or same creator. And of course, we notice this because when you do shuffling, you find that you get significant performance effects, for example, in K4 cross-validation. If you think of MNIST, right, MNIST stands for modified, and the original NIST data for digits of the same issue, and then we modify to make sure that he has some semblance of IID. Most of the data, of course, as said, are clean canonical as opposed to unusual real-world data examples. What do I mean by that? So often when we take pictures and post it on the web, these are unusual pictures that we see, right? These are not standard pictures that conform to well-known standard categories. And of course, a lot of well-curated data was the dirty, dinky data that we need to deal with. The issue, of course, is that adversary can do unusual things. Adversary is not bound by this IID assumption, can adaptively generate inputs, can query a learned model again and again, and learn from those queries and responses so as to adaptively generate different kinds of inputs so as to cause classification, misclassification, or targeted classification. So it's useful to think about taxonomies in different ways, right? So one is a threat model taxonomy. There are different taxonomies, of course. On the right-hand side, I have pointed a couple. So recent work from NIST, for example, led by Tabasi et al. It's slightly early work from Gilmer, which actually looks at taxonomy, motivation, constraint, and the abilities of plausible adversaries. What I'm showing here is something that we developed with Nicola Papernow back in 2016. The two axes, the y-axis shows you the amount of knowledge that the adversary has. Maybe a white box attack knows everything. An insider knows architecture, knows the training data, knows just about everything, all the way down to very little knowledge. But all the adversary can do is to query the black box with the input X, get an output Y, and then try and learn the model from that. On the X-axis, I'm showing adversary goals. So it could just be confidence reduction to misclassification to perhaps a targeted misclassification. So it's increasing complexity for the adversary goals, going from left to right, decreasing knowledge for the adversary, going from top to bottom on the y-axis. Okay, so why is it so easy to generate adversarial examples? I'll give you a simple example here. For illustrative purpose, I'm assuming that the loss function is smooth, continuous. Of course, none of the functions that deal with are, and that's not particularly important. You don't need to deal with with gradients. You can use pseudo gradients, for example. So you have an architecture with an unknown parameter theta. You've got inputs in, you've got outputs out, and you have a loss function now that measures the goodness of the model prediction on specific examples. In training is straightforward. You compute the derivative with respect to theta so as to, and then you adjust theta so as to decrease the loss function. What the adversary does is just a slight modification on that. You compute the derivative well with respect to the input because theta is fixed and adversary does not necessarily know theta. And then you update the input values so as to increase the loss function. Right? So instead of going down, you're trying to make your loss increase. And this is what, for example, the fast gradient sign method does. Right, very standard thing. You do you take a small step in the direction of the loss, in the direction of the gradient. It's very easy to generate adversarial examples, and which is why, of course, we suffer from some of these things. So let me spend a couple of minutes on taxonomy of defenses. Again, this is one taxonomy. There could be others. This is by no means exhaustive or exclusive. So looking at three different ways. So what do you do to the input? What do you do to the model? Can you give certificates? So the input one, so giving you a couple of examples out here. So papers by Ilyas and Sumit talk a little bit to that. So here the idea of the signal, the benign signal lives in a manifold. If you can identify the manifold, then I could perhaps measure distances of adversarial examples from that manifold and use that to measure how good the to detect adversarial example. Taken from paper by Susmija and others in INFERENCE 2018. So as I said, the idea is that first you need to figure out which embedding to use. You looked at different ones, LNE and isomorph, for example. You identify where the benign embeddings are. That gives you the notion of the signal manifold, and then you measure distances from that signal manifold for adversarial examples. Because the small details here, such as how do you measure distances, and what's the threshold to figure out what is benign, what is adversarial. And then the other work, for example, Shu and Buckman, they looked at notion of quantization. Idea being that if the perturbations are small, then it's probably the low bit that is getting corrupted. So if I could ignore that and and train my data on a quantized image, then perhaps I could get away with it. I could get away with suffering from adversarial perturbation. The notion of randomization is similar. That randomize some aspect, either the input or of architecture, and then look at what happens to your output. If your output remains stable across different perturbations, it is probably benign samples, or perhaps you could look at entropy. Right? Entropy is low, which means that your output was not affected by the shufflings. And if it is, then that's a good indication of some kind of adversarial attack out there. And there could also be model-based defenses. Generative models that come into play quite a bit recently. We did some work with Papernow on defensive distillation. Idea there was to have two models, one trained on the soft inputs of the first model. And of course, as with much of what's happening in defenses today, distillation now is shown to be vulnerable. There was a patch, tried a vulnerable fix, and so on and so forth, right? It's a continuously moving game. Why? Because we still don't have good models of how learning works. We talk a bit to the last thing out here, so certificate-based defenses. So here the idea is that, so I take an input text, I allow some small perturbation, and then I track it through this nonlinear network, of course, and to find out what happens to that input. Here I'm showing the patch as a square. So what happens to this, to the mapping of the output there, then you put some kind of a convex outer bound, and if the outer bound has not changed, gone across class boundaries, then you're safe, right? That's a basic idea. And again, with all the examples, I'm making it sound less sophisticated than the work actually, just as to give the underlying ideas. So with this background, in the next 15 minutes, I'm going to talk to 4 different pieces of work that my group has been involved in. So all of them are dealing with the notion of how do I protect myself from adversarial examples. The first one uses the notion of error correcting ideas to protect labels. The labels are what get misclassified. The second one, so this is all the present Europe's with Susceptible group. So this is about defining a new conference metric so as to detect adversarial examples. The third one says that contextual information is useful. That things don't happen by themselves, always context. If I can use that, then I may be able to detect adversarial examples. And the last one is on giving some theoretical bounds on membership, on how successful inference attacks might be. And if I have time after all 4 of these, I'll talk a bit to federated learning, adversarial federated learning. So it's a paper presented with Gunjan Verma at New York's last year, 2019. So idea comes from coding theory and communication. Right? So I'm showing you here a standard comms pipeline. You have an image that goes to a noisy channel, and you get a noisy output. And the goal is to reconstruct the input image X from the observed image Y on the right. And of course, what we do in standard comms, we do error correction coding. And the 3 ideas out here: redundancy, separation, independence, which of course info theory people know extremely well. So bottom one shows a machine learning pipeline, right? So again, here I have an input text that passes through this model of this machine ML model. And what I get out is really a summary, if you will. I get a probability of what that input image was as a class, right? If that image belonged to a tank class or car class or tractor class. So I'm looking at a summary image. So I want to infer properties. So how does error correction work here? So if we look at the adversarial examples we just discussed, noise has already been added to the image. So I can no longer protect that. Of course, we have the context and ideas that I talked to earlier. But we cannot code the input image. So what can we code? So that's the idea that we have. So the thing starts with looking at how standard deep neural networks work. So just showing a notion out here. Simple example of a 4-class problem. So these are all different airplanes, Airbus 320 and 3 different Embraer 190, Boeing 747. Of course, I guess none of us are traveling right now, so it's good to think about airplanes and think of the old days. So in standard DNN architectures, we use one-hot encoding, right? If the input is an Airbus 320, we want the output to be 1000, and so on. But what if I don't need to do that? So supposing I allow myself, instead of 4 outputs, I allow myself 8 outputs. And instead of looking for a pattern 1000 for 8320, I look for the pattern shown on the top, shown on the first row of this fat matrix out here. So matrix of all ones, vector of all ones, right? So this gives me some redundancy, right? And as you'll see in a second, it also gives me what's called code word separation. So if you recall, we look at distance between code words by Hamming distance, and what's the minimum distance between 2 code words, and that's what we call the Hamming distance code book. Right. So for standard one-hot coding, this is the code book we use, shown here as identity matrix, right? That's what one-hot coding does. And the Hamming distance between for this code book is 2. So Plotkin gives a general bond, an MN notebook. So this is M classes, and we have a n-bit code book. And typically it says that the Hamming distance is upper bounded by n/2, and times m/-1. And interesting result is that the wash Hadamard code achieves the upper bound. And this is the example that I showed you in the previous one. Right? Okay. So what this means is that I can get good code word separation. Why this is important? So changing 1 or 2 bits in the output, which is what you get due to perhaps the perturbations, will not change your classification output as it would do it if you use 1-bit coding, which is what we have with this with the standard architecture. The second idea we had also is that rather than just using softmax, which takes this the logit output zk and does this normalization, we could do these other things. You could use logistic, we could do tanh, but more important than that, since I have a code word, what I want to do is I want to take a dot product of what comes out of the sigma z, the modified logit, and I want to match filter that at the code word that I have for that particular output, right? In other words, I want to train z of c to resemble ck. In one-hot coding, you would train it so that you get 1 when that particular image is presented. So why do we do this? So here I'm showing you 2 bits. So the logic map for 2 bits. And what you see in the left-hand figure is the softmax decoder. So probably class 1 for binary classification, 2D logic space. And what you see is that this decoder is confident everywhere, right? High values, close to +1 or close to -1, except in this very small boundary region. What this means is that if I perturb the logic just a little bit, as shown in the rightmost figure, just a little bit, it goes across the boundary and you get misclassification. On the other hand, the sigmoid bit decoder, it's very confident only when there's agreement on both bits. So as shown in the top left and the bottom right corners. In between, it's got low confidence, it's got low certainty, which means also that you need a lot of perturbation to flip the class label out here. So the next figure shows that the demonstrates the same idea. The rightmost one shows you for a 30. So I'm showing you 3 bits of a 32 class classifier, and I'm using here Hadamard wash code of length 32. So there's no redundancy, right? 32 class, 32 bits, but I do get the coding gain. Right? I get a Hamming distance of 16 rather than 2, which I would get from I32 for the one-hot encoding. And again, you can see that perturbations are very difficult at the perturbation not easy class misclassification. Okay. The second idea we had is the following. So if you look at a standard architecture, all the outputs are trained at the same time, which means if an adversarial input, all of the outputs affected, which also means that you don't have this notion of independent errors across the outputs. Again, I'm just using analogy here to discuss this. So the output bits are highly correlated, which of course makes us suffer. So can you do something else? Our idea is that we break up the architecture instead of, let's say, for a 4-class problem, so learning all the 4-bit output at the same time. You train 2 different architectures. You learn 2 bits for one, you learn 2 bits for the other one. And of course, at presentation or test time, because you're going to present the example to both, and you're going to make a joint decision. But the notion is that because they're trained independently, your errors should be independent, and again, that makes you use some of those ideas from coding. So I'm showing you an example here, this which shows 2 things. One is that this the confidence measures that you get from a standard standard softmax decoder, standard architecture, are not to be, shall we say, should not be relied upon very much. So what am I showing here? So I'm showing this for MNIST, 10 classes, right? So for each of the 10 classes, what is the probability of the most probable class? So let's say I present a 3 to the input, it gets classified as a 3, then let's say probability of 0.9. So for each of those, then I can get a histogram across all the examples. Leftmost shows you the performance of benign. Most of them peak near 1, meaning that at least under benign conditions, all of them say 1, with high confidence, right? All of them give you the correct class and they're highly confident about it. The different ones out here, the pink is a softmax and the logistics. Then I have different encoders, different non-linearities I'm using. One is a TANH, the other one is a logistic. The 1610, 1632 refer to the length of the code I'm using, the Walsh-Adams code, already talked about. And then the ENS means whether or not I broke up the architecture. If I broke up the architecture, I'm calling it ENS. Sorry for the strange notation. And what this shows is that most of them work well under benign conditions. Okay, what happens when you have a bit of an attack? The standard PGD attack to norm epsilon physical 0.3. And so the middle panel in the top row shows you the performance. Again, I'm showing you the probability at the highest class. Notice that softmax, logistic, these are peak advanced, which means that they are confident even when they're wrong, right? They're very confident, tell us wrong things. Let's next take the example where I give it completely random inputs. Again, this is a MNIST architecture trained for MNIST, so it performs well, as seen in the leftmost panel. Then I give it random input, right? I give it a random image. What does it do? As you can see here, the 1032 works well. The TANH 16 works well. They both peak at low prob values, right? They're not confident at all. The others, like the Madri and the softmax, they are very confident even though they've been given random data, right? They give random data, they give you some digit. And so these confidence metrics need to be looked at with great care. In the bottom, I'm showing you that these architectures we have suggested, which is using this notion of breaking up the architecture, using different non-linearities. They work extremely well, even as we increase the perturbation strength. So the softmax, of course, as expected, performs worst. Madri shown here in the red curve, and our suggestions of using this broken architecture ends and TANH encoding with using 16 or 32-bit Walsh-Adams as opposed to 10-bit, gives you quite a bit of performance, as shown with this light blue and green curves out here. Okay, so let me show you a couple more performance examples. So what I'm showing here is for CFAR10, you got similar results for MNIST and FAST and MNIST. Showing a bunch of things out here. So left-hand side shows the models. Again, the 10, 16, 30 to 64 is the code length. So it gives some idea of the increased complexity of the architecture. The logistic of the TANH does not increase complexity. ENS means that the architecture broken up. The columns give you, the benign tells you what's the accuracy under benign conditions. Of course, high numbers are good. So most of them work well, as you can see. The PGD, CW, BSA column, these show you how often attacks fail. So again, high numbers are good. And DA RAND is when you give it, again, as I said earlier, when random inputs are presented to the model, how well does it do, right? And as you can see that even at the different kinds of attacks, our TANH, ENS 3216 models work extremely well. More importantly, the number of parameters we have in the architecture, 2 mil compared to 45 mil, that's a 20 reduction by order of 20. And with careful pruning, we can do even better than this. So for this part of the talk, just summarize this little bit. So going from softmax to sigmoid, it helped us quite a bit. It decreased the attack volume. Using this notion of Hadamard coding also helped us quite a bit. It constrained what the adversary could do. This notion of breaking with the architecture decreases the correlation of errors. And what we saw, of course, was that you don't sacrifice accuracy in the benign conditions. We want to give you all the caveats that we are not looked at scalability in the sense of we're not looked at 1,000-class problem yet. Other attacks exist, and I will come back to that in a minute or so. We could use different code books. We could also figure out how to split the architecture in different optimal ways. We have not done these work to BD. So I think I have only a few minutes, so let me quickly go over a couple of my other ideas we had. So I want to talk about this notion of attribution-based confidence metrics. And as we just saw with the Logit, that it's a very poor indicator of confidence, right? The Logit values are poorly calibrated. They don't correlate well. They don't predict accuracy well. So how can you measure the confidence of an architecture? So one way is, of course, related ideas that have been used in adversarial training by, for example, ideas put forth by Goodfellow and Madri and others. The notion is that I could sample a neighborhood of the input, then I could observe whether the model output has changed or whether it confirms the original output. But then the question is that accurately estimating the conformance of sample of the neighborhood becomes exponentially difficult with respect to the dimension of the space of the input space, right? So how do you sample well? So we need to sample efficiently, and we use this notion of integrated gradient, which was introduced in the DL literature maybe 2-3 years ago. And what this does is it gives you an idea of which attributes are important, and then based upon that, we do importance sampling. Right? So we sample the ones that are important we sample in the neighborhood that's more important, and we sample less often in neighborhoods that are less important. Let me give an example out here. So we have done work with both physical attacks and with digital attacks. The middle one shows the performance in middle on digital attacks, and the leftmost or rightmost show you performance of physical attacks. So here the idea is that you take, so how much of the data should we manipulate? So in this, I'm showing you when we take, we look at 0.2 to 0.4% of the data with the maximum attributions, which we sample in those, that's what we call masking, and then look at the number of label changes. And what we're showing on this figure out here is the number of label changes, proportional label changes. So low numbers are good, and of course in the original image, as you change the attributions, you expect to see little changes. And of course for the different kinds of attacks, you can see that they perform poorly, and that's shown in these two examples out here. Right. So what this means is that by looking at the number of label changes, I have now a way of detecting that an adversarial attack has occurred, and this shows that I can do so for different kinds of attacks. Right. I'm looking at FGSM, default, CW, PGD, all the standard attacks. Okay. Let me go next very quickly to the use of context. So this is some work we did with Shasha Lee, Srikant Krishnamurthy at UC Riverside. And the idea here is that objects don't occur in isolation. Objects occur in the context of an image. So here I'm showing a stop sign. So we saw the example before. You have a stop sign, you put a patch on it, you get it classified as something else, right? But stop sign does not occur by itself. Typically, there will be a zebra crossing nearby. There will be some other things in object in the scene. So then we can look at context in different ways. So context may be between parts of the same object, or between different parts of an object, different objects. For example, here the stop sign and the zebra crossing, between object in the background, what's in the background out here, and of course object overall scene out here. So we can build context in different ways. How do we learn the context? So details are given in the paper. I don't have time to discuss details, but we use benign data, we use autoencoders to learn learn the representation of the context. And then at text time, essentially, we see how different are the encodings between the benign profile and the profile that you get at test time. And again, it's a notion of finding distance between the benign profile and the learned profile. And this figure on the bottom kind of shows you that if there's separation, then you know that an attack has occurred, and there's no separation benign. The table just shows that we get good performance both in digital attacks as well as physical attacks. We looked at different data sets, compared with different benchmarks. Let me go quickly to membership inference attacks. So we talked a bit about that much earlier. And here the question is first, so what's a membership inference attack? So I have trained my model on a bunch of data. Adversary has access to a very larger data set, and it wants to know which subset of the data was used for training, or it wants to know, given this example, was it used for training or not? So the data set the adversary has is larger than the one that we used. And the top right, the equation on the top left gives me probability that the inference attack will make more than alpha prediction errors. Depends upon two things. It depends upon the intrinsic entropy of the data as well, that's H of D. Also depends on mutual information, ID, comma, Y. So this the information between the inputs and the outputs. And I can rewrite, and alpha, as I said, the number of errors you can make, card D is the size of the data set out there. And I can rewrite that in this fashion out here, shown here. So two things that you can see, of course, is that ideally you like to make the mutual information small so as to make the problem for the adversary more difficult. Yeah, of course, you could make mi equal to 0, but that means, of course, that you're not going to do any good in a classification. So the trade-off here, and what we did was we took the standard loss function, added a multiple of the mi, and then tried to minimize it. And the figure on the bottom right shows this. So it shows one is the unregulated and one is regulated, so which is regularized, where I use the mi as an added function, term to the loss function, and showing you two things. So here I'm showing that the regularization helps to decrease the mutual information. At the same time, we don't lose much in accuracy. Showing you performance here on 3 different data sets for 3 different attacks, and this against standard attacks. And what we see is that attacks succeed less often as MI decreases. And then what I'm showing on the bottommost table is a good correlation between the success probability and the mutual information. So key thing here is that, yeah, I would like to decrease MI so as to decrease the probability of success of an inference attack, and we show that indeed we can do so easily. I guess I should wrap up. So I was going to say a bit about federated learning. I will just do this one slide. So my motivation is very simple, right? I mean, most of the operations we do are in collision environments, which means that we don't work by ourselves. We have partners. Some of them partners we train with. Often the partners we don't train with. Maybe add a communities of interest. Often we get data from sources that we don't know about, that we don't know, own, control, or know about. So there may be a common goal that we want to train a common machine learning model. For example, perhaps we want to detect an IED, perhaps we want to detect a terrorist. But you may have policy constraints on sharing raw data, because sharing raw data often also tells you quite a bit about capability of a sensor. You may not want to do that. There may also be constraints and communication competition. Already talked about that earlier. On the other hand, we may not all the data, so you do want to do some sharing so as to improve what we can do. And finally, some of the machine learning goals may differ. The architecture I have may be very poor compared to architecture somebody else could afford. Machine learning goal will also be different. So we looked at different things, right? We can't send raw data, but we could do what, we could anonymize the data. We could do what are called sketches, summaries, core sets, or we could generate models from data that are synthetic. So since I don't have time to talk to, I'll skip past these 3-4 slides. I'll come to my last slide, which is what I mean by outlook. By this, I mean, what else should we do? So these, I think, are some of the problems we should be working on. And again, folks at my lab and some of the partner programs I mentioned are working on some of these. The first, of course, is that we don't have good models of learning, meaning we don't have analytical model what a machine learner does right now. If you could do, then you could perhaps characterize the complexity. We could figure out what are the inherent vulnerability. And of course, we need to quantify uncertainty, right? If there's some uncertain input, how do they get propagated to the output? How should we use that in a measure conference? How should that guide us in classification regression? We also don't have good enough realistic models of adversaries, right? I mean, we have either extremely strong, extremely weak. These epsilon norms may not be good enough to use, right? I mean, talked a bit about physical patch attacks, but we need to do more beyond that. And okay, I'll leave the slide up and then maybe just go to questions. So let me do that. Oops, I should perhaps stop sharing and then go to any question and answers that may be there.
Okay, thank you very much. So are there any questions? Okay, I have one small question actually. Related to your coding work, so how does your coding strategy affect the training time? Does it introduce extra overhead or?
Very good question. So maybe I should share my screen again and go back to the, shoot, what is this one? Okay. So let me see if you can get to that example I had. Okay, yeah. So let's look at this table I have here. So the number of outputs is increasing, let's say from 10 to 16 or 32. So one would think that that increases the training time. On the other hand, I'm doing two things. One, I'm showing here that the size of the architecture I have is actually much smaller. Right? And two, I'm doing this notion of breaking up the architecture into multiple pieces, both of which help me. So in the end, the amount of training time is not affected.
Okay, I see. So, but what if you have larger input dimensions and larger architectures, then it becomes important, right?
Right. So that's an excellent question. So two partial answers, as I said in one of my slides. So we have not looked at, for example, 1,000 class problems yet. But the first notion is that so even the standard loss functionality, but we're not encoding, you implicitly need to look at what happens across all the output nodes. So the extra complexity here is really in doing the match filtering, right? This multiplication, scalar product with what comes out and the code word. So I could still use a 1,000-bit output for a 1,000 class problem, but use Hadamard codes that gives me the added Hamming distance and perform well. So I think there will be a little bit increase, but not much. I could break up the architecture and save on that.
Okay, great. Thank you. So any other questions? I'm checking the session Q&A part meanwhile, and from the audience, any questions? Okay, if not, thank you very much. So really very good talk, and we appreciate your time. So I think we can, I can start sharing my screen.
Great. Thank you, Hulya.
Thank you very much. Okay, our second talk is by Yingying Chen, and so Yingying Chen is a professor at Rutgers University. She's also the associate director of Virus Information Network Lab, in short, WinLab. It's more famous. And also, she also leads the Data Analysis and Information Security Lab. She's a IEEE fellow. So she published lots of papers, and she received multiple best paper awards, including from Health IoT, CNS, SECON, Asia CCS, CNS, and Mobicom. She's also the recipient of NSF Career Award and Google Faculty Research Award. She also received New Jersey Inventor Hall of Fame Innovator Award, and also recipient of IEEE Region 1 Technical Innovation in Academic Award. Her research has also been reported in numerous media outlets. Today, she's not able to join us live, but we have a pre-recorded talk, and we will play it right now. If you have questions, you can always email to her, and she said that she would be more than happy to receive questions and reply back to you. I stop sharing, and maybe we can start playing the
I'll play
video.
the video.
Thank you.
Okay.
Hello, everyone. My name is Yingying Chen. I'm a professor.
Can you hear the audio?
Yes, we can hear, but the screen is very small. If you can make it large, it would be great. Okay, yeah, now it's good.
The audio, yeah, fine.
In the Electrical and Computer Engineering Department at Rutgers University, and I'm very happy here to provide my talk and to discuss my research work in this workshop. This workshop is very interesting, related to mission critical computation in edge devices using AI. And I hope my work that we look into the security vulnerabilities of voice assistants at the edge that can provide some insights for this workshop. I'm also an associate director at WinLab, which is called Wireless Information Network Lab. And I also serve as director for data analysis and information security lab. So just to give a brief overview of this lab has many researchers and faculties. We have about 20 faculties associated with this lab from different departments and with over 40 PhD students. And we provide internship opportunities every summer for graduate students, undergrad students, and also high school students. The graduate students and undergrad students could be from outside universities. And we work on many interesting research directions, including traditional delay-tolerant networks, mobile ad hoc networks, software-defined networks, and to the newer orbit testbed that we have the new research applications, including millimeter wave technology, healthcare, mobile healthcare domain, Internet of Things, and also in mobile sensing network coding area. Particularly, we try to deploy the orbit testbed, which we have funded by NSF since 2003 with $12 million. This has a 400 node USRP based node, and we try to deploy them into New York City. So about 2 years ago, WinLab is collaborating with Columbia University, New York University, and University of Arizona. We have attained the NSF Power grant with $22 million. And this one, the deployment, will happen in over 40 sites in New York City. And what we have is that we're also going to have the fiber connections to the Bush campus in Rutgers, at Rutgers. So many new research applications that previously we had imitating them on the orbit testbed could be fully tested using the 5G technologies, which provides very low latency for wireless communication. So we can look into the mobile healthcare domain, Internet of Things, and of course, to provide powerful edge computing and also future mobile internet to support many AR and VR applications. So to take a closer look, of the work that I like to focus for this talk is that the first part I'm going to talk about how to defeat the hidden voice command, that perform on edge voice assistance using the vibration signals by looking to the vibration domain. We know that the voice assistant systems have been deployed widely, not just at home, but in many public places, including our workspace. So those voice assistant systems, they provide capabilities, convenience at the edge for people to conduct daily activities, provide daily communications. And it also saves many scheduling related information and also have private information, many people's private information. However, we like to see that this voice assistant systems, they're actually vulnerable to hidden voice commands. So what is hidden voice commands? The hidden voice command is that those kind of command, the attackers, what they do is that they utilize the MFCC features. They extract the MFCC features from normal human commands, voice commands, and then they manipulate these MFCC parameters and to perform inverse MFCC, okay? And then they produce this obfuscated command. This obfuscated command, okay, when it's being played by a loudspeaker, okay, it could be recognized by the speech recognition systems. So they could be carried out by the speech recognition systems. However, it is hard to be understood by human ears. Okay, so this is what we call hidden voice commands. And some of the examples shown in the previous work, existing work, is that when the hidden voice commands, okay, could contain adversarial information. For example, it will ask the voice assistant systems to browse phishing websites, or for example, to conduct malicious command, for example, call 911, which is not being commanded by the humans, but it is being played by a loudspeaker, okay, from an attacker. So this is what we call the hidden voice command. And the hidden voice command also has the potential, okay, to ask the voice assistant systems to perform online shopping and payment without the notice of the human owners. So let's look at some of the related work. And usually, okay, to defeat the acoustic-based attacks, people looking into in the acoustic domain, okay, we're looking at to extract the speech vocal features, okay, or what we do is that we can look into the voice authentication model to set up voice authentication models. Okay. There are also another set of work that utilizes the speaker liveness detection. Okay. And our previous work, okay, tried to utilize to detect, okay, the sound to localize the sound signals, okay, that is being pronounced by the user's vocal cord, okay, in order to detect whether this is being played by a loudspeaker, the commands, or it is being said by a live speaker. So by looking at this, okay, in this work, what we can do, okay, the previous work, they only look into the speech audio features, okay, for the hidden voice command, to detect the hidden voice command. And what we like to do is that, okay, we like to see that whether it's possible, okay, we can look into a second modality, okay. We see the cross-validation, which is by looking to the vibration domain, adding into the acoustic domain to detect the attack. So in this approach, okay, we will not require, okay, the microphone to be held very close to the human mouth in order to perform, for example, the speaker liveness detection. So now basic idea is that there are many voice assistant systems, they actually equipped with motion sensors. Okay? The motion sensors actually help them to detect, okay, the direction, okay, of the voice commands, okay, and help them to orient, okay, to listen to the human commands better. So what we can do is that we try to look into the motion sensors that is attached to the voice assistant systems. Okay, and we will play back the command. Okay? In a very short domain, we can even partially play back the command. Either playback, we call the front end playback as the first command, is that, for example, to let the mobile device to repeat partial of the human command as the confirmation. Or we can let another approach is that we let the command, okay, being replayed in the cloud service. We call the back-end playback. Okay? And at the cloud service, we also have the motion sensor attached with cloud server, okay, to try to capture the sound being played back. So in our approach, okay, we want to see that whether, we can use the motion sensors to capture the voice commands. Actually, this is very challenging because motion sensors, they only be equipped with low sampling rate. Okay? And also, it has the nonlinear vibration responses, okay, to the audio signals. So what shall we do? Okay, we like to find the relationship between the audio domain to the vibration domain by derive this ILS relationship, nonlinear relationship. Okay. So why do we want to, take a step back, why do we want to look into the vibration domain? Okay. So the hidden voice command, actually, it's iterate when it's being generated, it is iteratively, adjusting the MFCC features, the voice features. So this kind of obfuscated command, although it could be still recognized by the speech recognition systems, but actually it must have something that has already been changed. And we think that the intuition is that the hidden voice command, the features, in comparing to the human commands, the features being captured by the vibration domain should be different. So that's why we look into the vibration domain, because it is hard to be forged from the audio signals. And it may present distinct vibration features. And also this resulting vibration responses could be device dependent, because each device, the motion sensors is unique. There are pre-existing work also have shown that. So in our system, what do? We can have two modes. Either we call the front-end playback or the back-end playback. So what we do is that we can look into the accelerator readings from the motion sensors, and we're going to perform the vibration noise reduction, and also the command segmentation. Then what we do is that in the vibration feature domain, we try to look into the statistic features in both time and frequency domain, and then use that, to combine with acoustic features. We try to extract acoustic features in the vibration domain also, which also utilized MFCC and also Cronach factor methods. And then we perform statistical analysis. Based on that, we actually apply machine learning methods. We applied both supervised machine learning methods and also unsupervised based classifiers. And you can see that we utilize the syncologistic method, random forest method, K-means cluster method. These are all very simple machine learning techniques. And we're happy to show that by just using simple classification method, it will be able for us to figure out the detection, the existence of the hidden voice command. And there's a nonlinear relationship. We derived the nonlinear relationship between the audio features and the vibration features. And we're happy to report here is that if you look into here, this shows the coefficients of some of the MFCC features. You can see that in the audio domain, the regular human voice, the human command, and the hidden voice command, they're clustered together, very hard to be distinguished. But if we look into the vibration domain, you will see that in the vibration domain, the human command is clearly separated from the hidden voice command, indicating that in the vibration domain, we have a possibility to detect the existence of the hidden voice command. So what we do is that in addition to the MFCC features, we we also look into the statistical features. So we have the combination of the statistical features in time and frequency domain, and also the acoustic features, okay, by looking into the motion sensor data, by looking into both the FFCC and Chrome vectors. Okay, and clearly you can see that, okay, by looking into the sum of the statistical features, when we have the different loudspeakers to play the hidden voice command and also the human speakers 1, 2, 3, you can see that they'll be clearly separated into 2 clusters. Okay, and this is the report of some of our statistical features in the vibration domain. Okay, and as we said in our system overview, that we have utilized the basic machine learning techniques, okay, to show the effectiveness of our approach. And I want to briefly talk about our experimental setup. So in our experimental setup, we have this front-end playback setup. So we utilize different smartphones, and then we have this different setup is that you can play the smartphone on the table. We utilize its voice and controllable systems, or we can put it on, use the hand to hold it, or put it on the sofa to see that what's the results we can get. And to simulate the back-end playback setup, so we imitate the cloud service device. Okay, we can have this onboard motion sensors, or we also implemented, prototype it by using the Raspberry Pi. And we have collected 13,000 vibration data traces, okay, in which, okay, 6,500 are benign commands, which are regular human voice command, and 6,500 are hidden voice commands. Okay, and this is showing our results. Okay, showing our results by using different simple machine learning techniques, and you can see that we can differentiate by adding the vibration domain. We can have 99% accuracy to different normal commands from the hidden voice commands. Okay. So the takeaways, okay, for this part, okay, we show that the voice assistant systems are vulnerable to hidden voice command. Okay? And we demonstrate is that we can add, in addition to the audio domain, we add a second domain, which is the vibration domain. And we utilize that vibration domain to help to secure the edge voice assistant systems, so that to protect the user's privacy. And this, we show that by using the vibration domain, okay, by using and relying on the simple machine learning techniques, we'll be able to detect the presence of the hidden voice command. So the second part of the work, okay, again, okay, it's still related to the voice assistant systems. I want to show that further, okay, in the voice assistant systems, when we're doing the speaker recognition system, okay, how we can perform adversarial attacks on top of it. Okay, so what is the speaker recognition system? Speaker recognition system is that when we do talk, okay, to a voice access control systems, to a smartphone, or even to a telephone banking, for all of this edge computing systems, and some of this, okay, are mission critical systems, tasks, and then we try to recognize who is speaking to the system. Okay? So this is on top of speech recognition. Okay? So this is more challenging to speech recognition. So in the speaker recognition, okay, many top speaker recognition systems, they utilize the deep neural network, okay, to have a better performance. And we like to see that the popular DNNs, the deep neural network, actually are vulnerable to adversarial examples. For example, okay, in the vision domain, people first find that in the vision domain, when you have a regular input of a panda, but once you add some small perturbation, the human eyes, we see it, it is still panda. We cannot see the difference. However, the deep neural network will recognize this as a given. It's a different animal. And the same thing happened, for example, in the stop sign. This is a stop sign, and if you add a very small perturbation, the human eye will still view this as stop sign, but with some small noise on it. However, once you add adversary examples to it, the adversarial machine learning will make this recognized as the speed limit 45. So this will be a horrible situation, right? If in the augmented reality applications, you recognize a stop sign as a speed limit 45, this will cause severe car accidents. So speaker recognition is an important, very important task. And the flow of the speaker recognition, what the attacks will do, the conventional attacks is that people will perform replay attack, synthesis attack or voice conversion attack. All of this, will be stopped at the model part, and this could be defended, at the modeling part. However, for the adversarial machine learning, it could fool the deep neural network, and then has to classify and perform the failure as the speaker. So the current adversarial attack, they can already successfully perform adversarial attack in digital domain. And in this work, we like to show that how we can perform a practical attack for over-the-air adversarial attack to the speaker recognition system. So this work, we like to show that we implement the gradient-based algorithms, and we look into the white box-based method, because many DNN actually, they posted their model online, so the model actually is public. It is gradient-based, and if you utilize that, you can implement the gradient-based method, and then to perform practical adversarial attack, to look into the multi-class speaker recognition system. And in the speaker recognition system, usually we call it as we have untargeted attack and a targeted attack. Untargeted attack is that attacker just want to pass the system, and you just recognize me as another legitimate user, then that is enough. This is usually applied to the criminal case. Well, targeted attack is that they want to do some specific attack. They wanted to attack a specific person. So what they do is that we call this as targeted attack. So given the time constraint, I will just go over quickly of this work, and if you have interest, you can look into our Hot Mobile paper this year. So we look into the multi-class speaker, and what we do is that we're going to attack this X-vector system. With X-vector system, it has the MFCC components, embedding model, and also the probabilistic linear discriminant analysis as the last step. So, as we said, this is a white box attack. So what we do is that we like to show that we're going to generate this F function, and utilize that F function, we can generate the noise or generate adversary samples that could perform the adversary attack, for both untargeted attack and targeted attack. So in our system, the attack overview is that what we want to do, is that you have the original audio, In the targeted attack, we're going to derive, the gradient loss, okay? And that could be part of our adversarial noise, and it generates adversarial example to play over the air to make the speaker recognition system fooled and then become the incorrect speaker. While for the targeted attack, we're going to iteratively working on the noise for the gradient descent method and then to generate adversarial noise. So this targeted attack is harder, it's more challenging, and it is the optimization problem. We provided as an optimization problem. Okay? So how we do over-the-air attack? Okay, we look into room impulse response. We look into the room impulse response, okay, that help us to first collect some information, okay, from environment, and then use that information to generate, to help us to perform the perturbation, okay, for both untargeted attack and also targeted attack. Okay, and in this work, okay, we look into the speaker recognition accuracy as our matrix, attack success rate, and also distortion matrix. So we look into the COPS data set, which has over 44,000 utterers, okay, spoken by over 100 English speakers. And we show some of our, first we show the results for the digital attacks, that is only attack the model, and then we will also show the results in our realistic implementation in both lab environment, both lab setup and also apartment setup. Okay, so we show that. Okay, so in our first work, we show that how we can detect the hidden voice command in the audio domain, okay, for the speech assistant systems, for the voice assistant systems in the edge. And in the second work, we show that how we can still perform practical adversarial attacks in the speaker recognition systems. So for this part, the defense part for the speaker recognition systems is still under study. It is a hot research topic. Okay, so in the future work, we show that the attacker could control your smart home by either using hidden voice commands or use the adversarial machine learning. And further, we want to look into the work is that if you're in the augmented reality world, right? So if the attacker, they can use to just inject some perturbations, it can give you wrong navigations, okay, and also can provide you incorrect information. Okay, so that actually could have many security issues to look into. And this kind of edge systems could be critical for the future augmented reality facilitated work that is in the mission critical tasks. Okay, thank you so much for listening to my talk. And I'd like to thanks to my collaborators and also students to achieve this interesting work to share with all of you. Thank you so much.
Okay, we also thank thank Professor Chen for her talk, and this is basically the end of the session and also end of the workshop. I would like to thank you for attending the workshop on behalf of all the organizers. So this is basically the end of it. Do you have any questions we can discuss? Otherwise, I think we can stop at this point.
Thank you, Hulya.
Thank you very much.
Thank you for the interesting talks.
Thank you very much. Okay, I think we can stop here, Noelia.
Yes, I'll stop the recording now.
Okay.